Welcome to today's session on the buck converter. So today we are going to take a look at some design parameters which are normally used to design a buck converter and indirectly used in asking different type of questions in exam scenario. We also try to take a look at the capacitor, assuming the capacitor is not large enough, and how to calculate the ripple voltage. And hopefully if we have time, we'll take a look at some example. The last time we met, we talked about the various currents through the inductor. We found the average, the minimum, the maximum, and we find some of the conditions which needs to be met to make sure that the inductor is operating in a continuous current mode. So today we are going to take a look at a design. Okay, the first one we want to take a look at is the peak-to-peak variation in the inductor current. This is a design parameter. A design parameter which is normally used in actual converter design. You want to keep that peak-to-peak variation, so inductor current going up and down. So that is the peak-to-peak variation. You want to keep that to a certain level. You want to keep this variation, which is basically the change in inductor current, change in IL. You want to keep that peak-to-peak variation to a certain level. We have the expression, let's go ahead and erase that. We have the expression for the change in inductor current for the two scenarios, when the switch is closed and when the switch is open. Let's take a look at one of them, which is here, which is for when the switch is closed. So that is a change in inductor current, and also we know the relationship between the output voltage and the input voltage for a buck converter, which is what we have stated over here. We are going to make some substitutions. So we are going to make some substitutions. So when we make change in IL, so basically this change in IL is what we have over here. Some of the substitutions we are going to make is replace T, which is the period, with 1 over F, and we are also going to replace S. So we have our source voltage. We are also going to replace our source voltage with VO over D, which is coming from the general expression for the buck converter. When you go through that mathematics and you do some analysis, you can come out with an expression solely involving the change in inductor current and the output voltage in relation to the inductance and the frequency, So that gives you a direct relationship between the output voltage, the inductance of your circuit, the frequency, the duty ratio, and the change in inductor current. If the change in inductor current is known or is fixed or want to be kept to a certain level, then it means you can design some of the other parameters, mainly the inductor, or what should be the frequency which needs to be used, assuming the inductor is fixed, assuming our output voltage is fixed. We want that output voltage across our load. What should be that inductor which we need to use to be able to maintain the change in IL, or what is the frequency which we need to operate this buck converter with, assuming that the inductor is fixed or is known to be able to maintain the change in IL. So that is one expression for the change in IL which you can use. You can also take this expression over here and make a substitution and find L. So when you do that, you get this expression over here, and you can go back to the original where we have the Vs over VO, Vs minus VO, and that also gives you this expression. So there are so many expressions you can play with. You can start with one and you can modify it as much as you like, but the objective over here is to find the relationship between the change in the inductor current to the inductor, the frequency, the duty ratio, or the output voltage, some of the parameters which we need to design for the buck converter. Let's go forward. Let's move this one up slightly and take a look at basically how the buck converter is operating. So before, when we started, we said we make an assumption that the components are ideal. So let's go ahead and erase that. So when we have ideal components, then the power supplied by the source should be equal to the power delivered to the load. In other words, Vs times Is should be equal to Vo times Io. When you manipulate this expression that we have over here, you come out with a nice expression over here. For those familiar with AC transformers, you are going to see that this is very similar to the VI, the voltage and current relationship for the AC transformer. What does this mean? In other words, this implies that the buck converter is basically a DC transformer. The buck converter is basically a DC transformer. Very good. The next subtopic we want to take a quick look at, let's bring this back and let's try to delete these ones here. The next subtopic we want to take a look at is the assumption that our capacitor is not large enough. So let's assume our capacitor is not large enough, which means that we are going to have some ripple voltage across our load. So that is the assumption we are making over here. The capacitor is not large enough. So if that is the case, don't forget before we came out with the KCL at this node, and that KCL is what? The sum of IC and IR should be equal to IL, which means that IC is equal to IL minus IR. So if IR is constant, we are still making the assumption that the current through the resistor is constant, which is the average current, right? So what is going to be the waveform for IC, knowing the waveform for IL? So to quickly refresh your mind, I'm going to go up slightly and take a look at the waveform for the buck converter, which is the current through the inductor. So when you look, let's erase some of this here. So when you look at this waveform, that is a waveform for the current through the inductor. Okay, the waveform of the current, which is the same as the average current through the load, is a straight line. That's what we have represented here by our straight line. The capacitor current, let's bring this one back. The capacitor current IC is basically equal to IL minus IR. So if our DC, if our current through the load is constant and we are subtracting that one from the inductor waveform, basically what we are doing over here is we are shifting this inductor waveform down. So we are now going to have our IC waveform with this being the zero axis. Okay, so basically this inductor waveform is being shifted down by how much? By the average current which is going through the load. So if we go back to where we were before, then the current which is going to flow through the capacitor is going to have this wave shape, and this is going to be 0 amps. So we are going to see that in one cycle we have the capacitor charging up, okay, when the current is positive. So far as the current is positive, we have the capacitor charging up. When the current is negative, we have the capacitor discharging. This is what is going to create the ripple across the output voltage. This is what is going to create the ripple. How do we calculate the ripple? Let's go back to basic definition of the capacitance. So we know that Q is equal to C times VO, which means that the change in Q should be equal to C times the change in VO if our capacitor is constant. From here we can find the expression for the change in VO, which is basically the change in Q over C. Now this is a region when the current through the capacitor is positive, so that's where the change is going to occur. If we can find this area, dividing that area by C is going to give us the expression for the change in voltage. This is basically the change in IL over 2, and I want you to go back to the original waveform for the inductor to convince yourself that this change here is actually equal to change in IL over 2. So we can use the area over here to find the change in Q, right? Which is half base times height. So half, that is the base, half of the period, okay, times the height, and the height is change in IL over 2. If you do that, then basically change in Q gives us that expression over here. Okay, this is the period multiplied by the change in IL over 8, which gives us an expression for the change in VO, which means we take that expression, we divide by C, and we get the change in the output voltage. Therefore, the change in the output voltage, if our capacitor is finite, is given by that expression. This is the change which is going to be shown or is going to be evident in the output voltage based on our capacitor value. And you are going to see very clearly that if this our capacitor value, let's go ahead and delete this one. From this expression, if this capacitor value C is actually infinite, which means very, very large, then basically this expression is going to go to 0, right? Because any number you have divided by infinity is going to be 0, which means that we are not going to have any change in the output voltage. But so far as we have a finite value of the capacitor, then we are going to have a change, and this is the expression we need to use when we are dealing with the buck converter to calculate the change in the output voltage. Let's go ahead and erase that. Okay, now let's find the expression for the change in IL. We have different expressions, right? So we have the expression when the switch is closed, and we also have the expression when the switch is open. That's up to you, but I have to just use one of them over here, which tells you the different formulas you can use when you are dealing with power electronics. So when we use the expression for the scenario when the switch is open, then that gives us the change in IL. When we substitute that expression, it gives us an expression for the change in the output voltage to be equal to that. One other expression we can calculate from this is known as the ripple. Okay, the ripple voltage. And how is the ripple voltage defined? So the ripple voltage is basically the change in the output voltage divided by the actual voltage, and that gives you what is known as the ripple voltage. So from this expression, change in output voltage to be equal to that. If you take the VO and bring it on the other side to divide, then that gives you an expression for what is known as the ripple voltage. That gives you an expression for what is known as the ripple voltage. Why is it important? Because sometimes in questions the ripple voltage might be given, or sometimes in question the ripple voltage might be one of the parameters we need when we are designing the buck converter. So it's very important. You are going to see that most of the time the ripple voltage is given instead of the change in the output voltage. If the ripple voltage is given a question, then you can take this expression or this formula we have over here, and then you can make C or L or F the subject. In this case, we want to make the capacitance as a function of the ripple voltage. So that is our C, and that is a function of the ripple voltage. That is a function of the ripple voltage. So if we are given a certain ripple voltage, then this is the value of the capacitor that is needed to be able to obtain that value for the ripple voltage for the buck converter, which is going to be defined. So this is going to end this session, and the next time we come back, we are going to take a very quick look at an example under the buck converter to try to sum everything that we've done under the buck converter to a close. Thank you.